A model can look like it has learned something even when it has not learned anything at all. Open one local chat and tell the model, from now on, whatever I type, reply with exactly one short joke. Inside that conversation, the model may follow the instruction perfectly, but open a fresh chat with the same model and the model goes back to giving normal answers. That is the difference this video is about. Prompting changes one conversation. Fine-tuning creates a repeatable model behavior. But making that behavior repeatable is only the first part. In this experiment, the fine-tuning run finished in about 5 minutes, yet deployment exposed architecture errors, missing chat formatting, context limits, and a cloud fallback that initially looked like local success. By the end, you will know when fine-tuning is the right tool, which MLX method fits your hardware, how to read the important terminal logs, and how to verify that the final model is actually running locally inside your workflow. For the first test, I used the original Qwen 2.5 MLX community model inside Ollama. It loaded correctly and gave normal answers. I added the joke instruction in one chat and it followed it. In a fresh chat, the behavior disappeared because the instruction was no longer in the conversation history. The model weights had never changed. Before changing any weights, decide whether fine-tuning matches the problem. Use prompting when the instruction changes from task to task. Use retrieval when the model needs current facts from documents, policies, prices, or inventory. Use fine-tuning when the desired behavior, tone, classification rule, or output format should remain consistent across fresh requests. A one-line joke behavior was deliberately simple, so any change would be easy to observe and measure. This is where MLX becomes useful. MLX is Apple's machine learning framework for Apple Silicon, and MLXLM is its language model toolkit. It let me fine-tune the model, compare checkpoints, fuse the result, and test it directly. I used Qwen 2.5 instruct in BF16 precision. Parameters are the learned numbers that shape a model's predictions. This one has roughly 494 million. BF16 stores each parameter using 16 bits and provides a wide numerical range for fine-tuning. The model was small enough to run this experiment on an M1 Mac with 16 gigabytes of unified memory. The dataset contained 125 fine-tuning examples, 24 validation examples, and 24 held-back tests. Each paired a normal request with one short, topic-aware joke. The first split taught the adapter, the second checked progress during the run, and the hidden test split measured the selected result on unseen prompts. This small dataset worked because the behavior was narrow. For a business workflow, coverage matters more than simply collecting more rows. Include normal cases, edge cases, different writing styles, and examples of what the model should refuse or leave unchanged. MLXLM offers three main fine-tuning types: LoRA, DORA, and full fine-tuning. LoRA freezes the base model and learns a compact correction called an adapter. DORA also uses an adapter, but separates updates into direction and magnitude. It can improve some tasks at the cost of extra computation. Full fine-tuning updates the model weights directly, giving more freedom but requiring more memory, data, and evaluation. QLoRA is not a separate fourth option. It means using LoRA with a quantized base model. That saves memory but adds reduced precision as another variable. I chose regular LoRA on BF16 because this was one narrow behavior on a 16 gigabyte Mac. It kept the base weights frozen, made checkpoints easy to compare, and made only about 2.9 million parameters trainable, or 0.594% of the model. The adapter used rank 8 across 16 layers. Rank controls how much capacity it has to represent the new behavior. A batch size of 4 meant 4 examples contributed to each update. The learning rate controlled the size of that update, and a fixed seed made the run easier to reproduce. Over 600 steps, MLX evaluated and saved a checkpoint every 100. A checkpoint is the adapter captured at one moment. The last is not automatically the best. The terminal called its error score train loss. Here, that meant the LoRA fine-tuning loss, and lower was generally better within the same experiment. It fell from about 2.87 to 0.10, showing that the adapter was fitting its examples. Validation loss improved from about 5.60 to 1.52 at step 100, then rose to roughly 2.22 by step 600. The adapter kept improving on familiar examples while becoming worse on unseen ones. That is overfitting. I compared steps 100 and 600 with the same prompt at temperature 0, which kept generation repeatable. Step 100 produced the cleaner joke and the best validation result, so I selected it. The terminal's trained tokens value reached roughly 124,000. That meant cumulative token positions processed during fine-tuning, not new words learned from scratch. The test command also reported loss and perplexity, a measure of prediction uncertainty, but the response still had to satisfy the behavior we wanted. The run took about 5 minutes, with peak MLX memory near 1.8 gigabytes. That was not the max complete memory use. Fresh prompts worked when I loaded the selected adapter, proving that the behavior no longer depended on old chat history. I then fused the adapter into the base weights to create a standalone BF16 safe tensors model. Fusion combined the learned correction with the original weights. It did not change the architecture or quantize it. Safe tensors stores the model, but a compatible runtime is still required to execute it. At this point, the fine-tuning experiment was complete, but the deployment experiment was not. A model can work in one runtime and fail in another because each runtime handles architecture files, precision, prompt templates, context metadata, and request settings differently. That is why I tested 3 layers: OMLX for exact MLX native API serving, Ollama for widely used local model packaging, and Hermes for integration inside an agent application. This distinction shows whether a failure came from the learned behavior, the serving runtime, or the application configuration. For an MLX native service, the cleanest route was OMLX because it served the exact fused BF16 folder through an OpenAI compatible API. That means other applications can send a familiar chat request while the model runs locally. For a developer building a private ticket classifier or CRM summarizer on Apple Silicon, this is the shortest route from the fused model to a local API. 4 independent requests reproduced the behavior without attaching an adapter, changing precision, or converting the model. Ollama exposed a different serving boundary. Its direct MLX route accepted the fused safe tensors files, but inference failed with unsupported architecture. Registration only proved that Ollama had stored the files. The original Qwen package worked in Ollama, and the fused model worked in MLX-LM and OMLX, so the failure was specific to this fused export and loading path, not the whole Qwen family. A model file pointing to the fused directory provided the better route. Ollama converted it into an internal F16 GGUF and served it through llama-server, bypassing the incompatible direct MLX route. GGUF is a model container, and F16 still uses 16-bit weights, so this changed packaging rather than applying 4-bit quantization. For an individual or small team whose desktop chat or automation already connects to Ollama, this makes the model reusable without writing a custom MLX service. It also avoided an unnecessary manual FP16 copy and external conversion. The converted model loaded, but its first answer began like a joke and then rambled. The weights were active, while the conversation formatting was wrong. The exported configuration lacked the complete chat template Qwen needed to mark user turns, assistant turns, and stopping. Adding Qwen's chatmel template restored one-line answers and a normal stop signal. The runtime also keeps a KV cache containing attention information from the current conversation. Quantizing model weights does not automatically shrink this cache, which is one reason long conversations can still consume substantial memory. The final layer was Hermes agent. This test was for people who want the model inside an agent workflow, for example, an assistant that receives meeting notes calls a business tool, and prepares a CRM entry. Here, success means more than producing the right text in a terminal. The model alias, provider, context, reasoning settings, and fallback behavior must also be correct. Context is the amount of conversation a model can consider at once. Hermes requires providers to advertise at least 64,000 tokens, while this Qwen model natively declares 32,768 positions, so both local providers were rejected before inference. For this short demonstration, I added 64K compatibility metadata to OMLX and a separate 65,536 token Ollama wrapper. This cleared Hermes' guard, but did not turn Qwen into a proven 64K model. The responsible use remains short prompts in fresh sessions. Then Hermes sent Ollama its default medium reasoning setting that asks the provider for a dedicated thinking feature, which this Qwen model does not implement. Ollama returned an unsupported thinking error, and Hermes switched to my other default model. The polished invoice explanation therefore came from the fallback, not from my local model. The correct route was a fresh chat followed by /reasoning none, then selecting the exact local alias. This disabled reasoning for that session and let the request reach the non-reasoning model. OMLX is confirmed end-to-end in Hermes and returned. An invoice is a promise wrapped in a receipt. Ollama produced the expected joke with the equivalent think: false request, but its desktop Hermes path remains conditional until the same sequence finishes without a fallback banner. The final route was evidence-driven at every stage. A BF16 base for a clean learning signal, LoRA for an efficient behavior change, step 100 because validation, and output quality beat, step 600, fusion only after adapter verification, OMLX for direct BF16 serving, Ollama's model file conversion with the correct chat ML template, and fresh Hermes sessions with reasoning disabled. The joke is the visible proof. The reusable workflow is to define one behavior, keep evaluation data separate, compare the available methods, choose each checkpoint and runtime from evidence, and repeat the same prompt at every serving boundary. Prompting changes the current context. Fine-tuning makes the behavior repeatable.